Hi, and welcome to our second lesson on polynomial functions and their graphs. Today's lesson is relatively small. You want to have lots of time and lots of thought put into solving polynomials in school tomorrow. So, as you look at the four graphs that are shown here, along with their function rules beneath, I'd like you to do what it says. Take a look at graph and function rule and see if you can come up with some idea about the degree of a polynomial function and the number of turning points that the graph will have. Let's pause that video and think about that. Alright, I would assume that many of you have already come up with this conclusion. The degree 1 graph had no turning points. The degree 2 graph had 1, etc. The degree 3 had 1, 2 turning points. And the rule is the graph of any polynomial function of degree n will have at most n minus 1 turning points. So if we're talking about a 5th degree polynomial, the most turns it can have is 4. Okay? This is going to help us as we're graphing, and that is our goal today, to be able to graph polynomial functions. We have a plan. If you've know me at all, you'll know that I like plans, and this is a plan for graphing a polynomial. So it says that we should first use a leading coefficient test too, and that's determine end behavior. Okay? Determine end behavior. We can find x-intercepts by setting the function equal to 0 and solving. And as far as methods for solving, the idea is we factor and set each factor equal to 0. Reminding that we should check for multiplicity. Some roots may occur more than once. You find the y-intercept by, there are two methods really. You can either multiply out the polynomial and look at the constant, or set x equal to 0 and solve for y. Next, you'll want to think, I hope, about the symmetry. If a function rule has all even exponents, that means the graph will reflect over the y-axis. That would be an even function. If a function rule has all odd exponents and no constant, we need to add that here. If it has all odd exponents with no constant, that means the graph will rotate about the origin 180 degrees. Use the degree to determine the number of turning points. And you probably will have to locate turning points by looking at a table. Don't forget that the table will help you with that intermediate value theorem, which tells you that when the table changes from positive to negative or vice versa, you've isolated a root. Intermediate value theorem. Remember, you can find values for turning points, maximums or minimums, using second trace, max or min. And that's a pretty good strategy right there for graphing a polynomial function. Let's apply it. Alright, we're going to graph the polynomial x to the 4th power minus 2x squared plus 1. What I would ask you to do is answer these questions before you hear my result. That is, I would pause the video right now and say, what's the end behavior? Positive leading coefficient and 4th power, so we should be up, up. x-intercepts, well, we got to figure that out. So we need 0 equals x to the 4th minus 2x squared plus 1. I believe that we can factor this. Yeah. Even though it's a 4th degree, we still can apply the factoring patterns. It's just that we'll get x squared stuff instead of just x stuff. But we need to add things that multiply to make 1 but add to make -2. And that would be -1 and -1. So this thing factors this way. X squared minus 1 times x squared minus 1. Both of these factor using the difference of squares pattern, because that's a perfect square and that's a perfect square. We get x plus 1, x minus 1. That's from that first. The second parenthesis is going to have the same factoring, x plus 1, x minus 1. And our x-intercepts then will be 1 and -1, and each of them have multiplicity 2. See, that tells us something, because when we hit those roots, we're going to bounce, right? We're going to have up behavior, up end behavior. We're going to have x-intercepts at 1 and -1, and those are going to be bounce spots. The y-intercept, this function is already multiplied out, so the constant is the y-intercept. It's going to hit the y-axis at 1. Does it have symmetry? Yep, this one is even, so it should reflect. And since it is a 4th degree polynomial, it will have at most 3 turning points. Alright, I think I can see where they have to be. If we're going to be up behaviors, we got to come down, hit this root, and bounce because it had a multiplicity of 2. There's one turn, there's the second, hit here and bounce. And that's what that function's got to look like. Now, I want to just check that, so I'm going to bring my calculator up and graph that function. And there it is. Boy, we did pretty good on that one. We've got a function that looks just like it's supposed to look. Okay, that's it for today. We're going to ask you to get out there, try the U-Try, and we'll see you in school.